Concentration and rate. We can learn important information about the reaction by examining how the initial rate of the reaction changes as we change the concentrations of various reactants. This is what we do in a rate experiment. Here are the results of a series of experiments for the reaction between NH4+, ammonium ion, and NO2- nitrate ion, both in a water solution, to produce N2 gas and liquid water. We have measured the initial concentrations of each ion and the initial rate of the reaction, probably by measuring either the volume of N2 gas produced at a constant pressure or by measuring the pressure of the gas at constant volume. If we look at the first four experiments, we see that the concentration of NO2- does not change, while the concentration of NH4+ does change. So any change in the initial rate of the reaction must be due to the change in the initial concentration of NH4+. Looking at experiments 1 and 2, we see that when the concentration of NH4 doubles, the initial rate doubles as well. Picking any other pair of the first four, we see the same kind of relationship. For example, in looking at experiments 2 and 4, the concentration triples, and so does the rate. In experiments 5 through 8, the concentration of NO2- changes, while the concentration of NH4+ does not. So any change in the initial rate of the reaction must be due to the change in initial concentration of NO2-. In experiments 5 and 6, the concentration of NO2- doubles, and the initial rate doubles. Again, we see a similar kind of relationship in any pair of these experiments. For example, in experiments 6 and 7, the concentration of NO2- is multiplied by a factor of 1.5, and the rate is multiplied by a factor of 1.5 as well. This means that the rate of the reaction is proportional to the concentration of ammonium ion if the concentration of nitrite ion is constant, and the rate of the reaction is proportional to the concentration of nitrite ion if the concentration of ammonium ion is constant. If the rate is proportional to both ion concentrations, then it is proportional to the product of the two. This is more generally written, rate equals K times the concentration of NH4+ times the concentration of NO2-. This mathematical expression is called the rate law, or rate expression, or rate law expression. And the constant K is called the rate constant. The rate law shows the relationship between the rate of the reaction and the concentration of each reactant. This relationship is called the order of the reaction in the reactant and is given by the exponent of the concentration. So the reaction is first order in the concentration of NH4+ because the exponent is 1, and also first order in the concentration of NO2- because the exponent is also 1. The overall order of the reaction is the sum of the exponents. So overall, the reaction is second order. For a general reaction like this one, A plus 2B plus 3C gives D plus 2E. The general form of the rate law expression is rate equals K, the rate constant, times the concentration of A to the power alpha, times the concentration of B to the power beta, times the concentration of C to the power gamma. Alpha, beta, and gamma are the exponents, which must be determined experimentally. They may or may not correspond to the coefficients of the equation. You should note two things about this expression. First, it includes each of the reactants, no matter how many there are. Second, the value and units of K will depend on the overall order of the reaction. The units of the rate are molar per time, which must be the same as the units of K times molar raised to the alpha plus beta plus gamma power. Let's do this sample problem to see how these things work out. The data for 3 experiments are given for the reaction A plus B gives C. Let's determine the rate expression for the reaction. When we do this, we want to choose experiments where one of the reactants changes and the others do not. If we look at experiments 1 and 2, we see that the concentration of A does not change, while the concentration of B doubles. However, the rate of the reaction does not change. This means that the reaction is zero order in B. This means that the rate of the reaction does not depend on the concentration of B. Remember that anything raised to the 0 power is 1. If we look at experiments 1 and 3, we see that the concentration of B does not change, while the concentration of A doubles. The rate is 4 times as great, so the reaction is second order in the concentration of A. 4 times the rate is the doubled concentration squared. So the rate law expression is rate equals K times the concentration of A squared times the concentration of B to the 0 power, or simply rate equals K times the concentration of A squared. A common thing to calculate is the value of the rate constant and the units. If we plug the values for one of the experiments into the form of the rate law expression, we can calculate K. If we use the values from experiment 1, we have 4.0 times 10 to the minus 5th molar per second equals K times 0.100 molar squared. So 4.0 times 10 to the minus 5th molar per second divided by 0.0100 molar squared equals K. So K equals 4.0 times 10 to the minus 3rd molar to the minus 1 seconds to the minus 1. An interesting point is that it should not matter which experiment we use. We should get the same value for K for each of the experiments. So an interesting check is to use a different experiment's values to see if the same value of K is produced. If not, then a mistake has been made in the rate law expression. Once we know the form of the rate law expression and the value of K, we can find the initial rate of the reaction with some other initial concentrations. We simply plug the concentrations and the value of K into the rate law expression. Note that we can ignore the concentration of B because it is 0 order, and calculate the answer.